This video is an introduction to thinking about circuits that have parallel resistors. So first, here is a diagram of a very simple parallel resistor problem. I've got one voltage source that's an ideal battery, so no internal resistance. And then it's connected to two resistors, R1 and R2, in general can have different values of resistance, but very carefully I'd like you to see that these two things are in parallel. So as a contrast, imagine the series combination of the two things, right? So this is just in contrast. This right here is in series, and this is in parallel. And if I have R1 and R2 oriented this way, I'd like you to notice a really big difference. If I was to count conductors that are completely separate from each other, I've got this conductor, I've got this conductor, and I've got a third conductor. Goes all the way around back here. So I've got three conductors. But over here, I actually only have two conductors. I've got the conductor that's connected to the bottom of the battery. Can you see this is all one piece of metal? So if it's all one wire, that means it's only got one value of potential. But then I have another conductor connected to the top side of the battery. So this is all one piece of metal. It's one big equipotential space, right? So everywhere along the upper wire is one value of potential, and everywhere along the lower wire is another value of potential. Potential and current aren't the same thing. So what's interesting is, in this circuit, which I described in the previous video, you only have one current, I, and the same current travels through the resistor, through this wire, through this resistor, along this wire, around this corner, right, around this corner, and also through this battery. It's all the same current, all at the same time. But this one actually has two different currents, or three different currents, depending on how you're counting. But the point is I'm going to have a current that rounds around the corner, and this corner right here, and I'll call that current I. But when this current gets here, at this junction, it actually can split into two parts, which is a lot like the highway example I gave in a much earlier video. So this current goes through this resistor. Maybe I'll call it I1 because it's the current that goes through resistor number 1. And this other current goes through R2 instead, so I'll call it a different name because in general it won't have the same value, right? And this current rounds the corner, comes, and the thing is though, is these two currents rejoin at the junction to remake the current I. And so charge conservation tells us that at the first junction right here, the current that enters the junction needs to leave it. So the current going into the junction is I. And the current leaving it, though, is I1 and I2. So the and is a plus sign. And then at the second junction, I get the current coming into the junction is a combination of two, right? I1 comes into the junction and I2 comes into the junction. And what leaves the junction is I. So these two junctions actually predict the same relationship. But anyways, I only have, right? So in series, I actually have multiple currents, right? I've got I1, I2, where I1 and I2 and I have a very particular relationship, right? An algebraic equal sign relationship. But in series, I only have one potential difference. But in the series case over here, let me draw a line. In the series case, I actually have two potential differences. Right? I've got the potential difference between blue and red, and then I have the potential difference between red and green. So there's two potential differences. But what I also have is only one current. Can you see that these are very different types of circuits? So there's big differences between the series sorry, this I meant to say parallel. Excuse me. In parallel circuits, sorry. And over here is the series. So they have very different setups, very different things going on. Okay, so let me move on and talk more about this parallel circuit. So another thing about parallel circuits is I'd like to be very clear about something. So I drew the circuit above to look like this. R1 is on the left and R2 is on the right. And it looks like this. But this is actually equivalent to the following circuit. You could draw it this way. So I'm going to draw this like weird diamond shape, but I'm going to be really careful while I draw it. So I'm going to keep R2 on the right side. It actually doesn't matter. You just have to, talk about the right current on the right leg. But I'm going to draw R1 down here. And then I'll rejoin them. This circuit that I just drew is identical to the one on the left. It's got the same circuit characteristics. And you could even morph or change the shape of the wires. As long as you don't cut a wire, you can change its shape to look like anything you want, right? And as long as you don't make any new connections, any new welds, but you can bend the wires and you can stretch them and distort them. You just can't cross them. You can't cut them, right? So here's another example. So this circuit right here is another way to draw the very same thing, right? So put R1, R2, and here's even another one. This one is just for fun, mostly. Let's put R1 here and put R2 here. They're going to end up having to be connected. Whoops. So they're going to have to end up being connected to the battery on the back, but I'm going to connect them right before. Yeah, so this is also equivalent circuit. So the wires aren't necessarily straight, there's curved parts to it. But the point is it's all about what's connected to what, right? So these are all equivalent. I just bent and changed wires around. So let me, though, it turns out it's kind of the easiest. You sort of see through the circuit the fastest way if you draw it this way. And the reason is because you can identify the conductors really simply and quickly. So I'm going to say, that there is a conductor up here. I'm going to call it the red one. It's all this single piece of wire, right? And then I have another conductor. I can call it the blue one, right? And there's only one potential difference. It's between red and blue, and it's actually provided by the battery. I'm guaranteed that, right? So, yeah. So if you look, and this is R1 and R2, you can see that the voltage across R1 is V. right? Because the voltage across R1 is between red and blue. And the voltage across R2 is the same. It's just V, right? So I only have a single value of potential difference, right? It's just V. But V, the voltage across R1 tells me about the current in R1 this way. So the voltage across R1 is the current through R1 times the resistance of R1. So I'm going to say that there's a current called I1. There's a current that's called I2 here. It flows from the high side to the low side, so I drew both currents going downwards. And that is multiplies to be the same value. Okay, now one last thing is the junction rule for the currents. Remember that this was true, right? This is just charge conservation. So what I'm going to do is I'm going to take this equation and I'm going to solve for I1 and I'm going to put it there. So if I solve for I1, it'll be V over R1. So what fits right here is V over R1. And then adding to that is a similar thing for I2. Like right here, if I solve for I2, you just get V over R2. And this is called I, all right? So I is the, you might say it's the circuit current. It's the total current in the circuit. And there are branches in the circuit where that current gets split. Part of it goes through one resistor and the other part goes through the other resistor. So the aim, what I want to show you is I'd like to re-understand this circuit this way. I'd like to say that somehow these two resistors over here inside this dotted line, I can just represent them by a single equivalent resistance. And so if I've got V here, there's going to be a current I that flows through this equivalent resistance. And Ohm's law says that V equals to I times the equivalent resistance. So what I'm going to do is I'm actually going to solve for I, right? If you solve for I here, it's equal to V over the equivalent resistance. And now this is why I did this. If you do this, V over R equivalent equals V over R1 plus V over R2. What this implies is R equivalent, the inverse of it, is 1 over R1 plus 1 over R2. And this is called the parallel rule. It can be extended. If you have, here is a power supply, and what I'm going to do is imagine creating a lot or multiple parallel connections between the upper conductor and the lower conductor. And I'm going to say that what's going on is, let's say R1, R2, like lots of them, and then this will be Rn. So I have N resistors in parallel, all connected in parallel to a battery V. So this is a purely parallel combination. You can rewrite this as an equivalent resistance where R equivalent, 1 over it, is the sum of all of the individual resistors, I equals 1 up to N, but you have to add their inverses. Something that you can actually do is you can prove that this is algebraically the same as the product of all N resistances divided by the sum of all N resistances. So you can do it either way. If you remember, this looks like the capacitors in series rule. We actually used really similar kinds of arguments. that the potential difference across every capacitor was the same, right? That the way the charge separates is such that the charges have to, that the net charge is 0, right? So it's a charge conservation and a potential difference sort of rule set. Yeah, so capacitors in series. Problem is most circuits have mixtures of parallel and series. And those kinds of problems, what they look like is this. You might say that I have a power supply. There is some sort of internal resistance. Here is the EMF, right? So already I have a resistor, and I'm going to connect this in parallel with this load. That is this strange combination. Actually, let me not make it that strange. Let's do this, right? And the goal next is to figure out how to solve these kinds of problems, right? So if you look at this, what I would do is first realize that these are in series. And so what I'll do is I'll figure out an equivalent resistance for that series problem. And what this morphs into then looks like the following. I've still got the EMF, the little r internal, but now I've got the parallel combination of this thing called R1 and this thing called RA, right? So now what I'll do is I'll realize that this is a parallel combination. So I'll do the parallel combination of R1 and RA. And then if I redraw my circuit now, it looks like this. So here is the EMF, and this is R internal. And I have combined in parallel something that I'm going to replace with R sub B. Oops. Right? And then what I'm going to do is realize that R internal and R sub B are in series. So I'll have a further equivalent resistance called RC, which is the series combination of R internal and RB. And you can see how this builds up, right? It's an iterative, it's honestly, it's like a, for computer scientists, this is a recursion. You're building something up recursively. So you go all the way down to the simplest combination that you can find, which was this original series here. And then you come back up out of the bottom and look at less, or yeah, so you combine those problems. Okay. All right, so, okay. So this is R internal plus RB, and RB is R1 times RA over R1 plus RA, right? That's the parallel combination rule. And RA is just R2 plus R3, right? And so you can just go, now you know RA, it sits right here. And now you know RB, it sits right here. And now you know RC. And with RC, you can get the circuit current. It's the current that travels through our EMF over here. It actually is the same current that flows through our internal. But this current, when it gets to this first junction, it actually takes two paths, and you can say that that splits into an I1 and also an IA, where IA is imagined to flow through R2 and R3, right? So this is one way you can imagine building up solving this problem. Okay.